Now let us derive an expression for the velocity and acceleration of a fluid at any point. This is important to derive an expression for velocity as well as acceleration of a fluid at any point. To understand this, let us have u, v, and w. So these are the velocities. Velocity components in x, y, and z directions. So the velocity components are the function of space coordinates and time here. So what we can write down is u is a function of, you can write f1 is a function of x, y, and z direction with respect to t and t. V can be written as f2 is equal to x, y, and z t, and w also can be function of written as x, y, and z into t. Now the resultant velocity can be written as v is equal to ui plus vj plus wk. So this can be written as root of u square plus v square plus w square. So this is the resultant velocity. Now let us consider acceleration. Acceleration, that is the total acceleration, is ax, ay, and az in x, y, and z direction. Now let us follow a chain rule of differentiation. So if we follow chain rule of differentiation, what do we get is, now let us take acceleration in x direction. So this can be written as ax is equal to change of velocity with respect to time. So du is nothing but velocity, change in velocity with respect to time. So it can be written as, so acceleration is what? Change in velocity with respect to time. By using chain rule of differentiation, we can write this particular thing as dou by dou x into dx by dt plus dou u by dou y into dy by dt plus dou u by dou z into dz by dt plus dou u by dou t. Now we know that dx by dt will be nothing but u, and dy by dt is nothing but v, the velocity in v direction, and change in dz by dt is equal to w. So this is the same, you can refer the continuity equation problem for this to understand dx by dt is equal to u, dy by dt is equal to v, and dz by dt is equal to w. So this is nothing but change in the displacement, that is dx with respect to time is nothing but the velocity. So again, displacement by time, velocity in y component or y direction, and change in velocity of in z direction is nothing but, sorry, change in displacement in z direction will get velocity in w or z direction here. Now therefore we can write this as ax is equal to du by dt, that is equal to u dou u by dou x plus v dou u by dou y plus w dou u by dou z plus dou u by dou t. Similarly, we can write this thing in y direction as well, that is nothing but dv by dt, that is equal to u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z plus dou v by dou t. And similarly in z direction, same thing, dw by dt by using chain rule. By using chain rule, we can write this as u into dou w by dou x plus v dou w by dou y plus w into dou w by dou z plus dou w by dou t. Okay, so this is the equation that we get for acceleration. Now let us apply this equation for a steady flow. If you have to apply it for a steady flow, what does it mean is that dou v with respect to time is equal to 0, that is the resultant velocity, where v is a velocity, is equal to 0 here. So what do we get here? So steady flow is that, what we get here is that dou u by dou t is equal to 0 into dou v by dou t again is equal to 0, and dou w by dou t is equal to 0. So for steady flow, you need to cancel all this out to get the equation for acceleration in a steady flow. The acceleration vector can be written as a is equal to axi plus ayj small j plus azk. This can be written as root of ax square plus ay square plus az square. Az square.